The content presented is offered through Statistica Hub. Your support sustains Statistica Hub's commitment to providing high-quality educational resources for free through its open course programs. Explore additional courses on the Statistica Hub platform at www.statisticahub.com.
Hello everybody, welcome back to the lecture 7 of Bayesian Inference. So in the previous lecture we have discussed about Bayes theorem for events, and I told you that in the upcoming lecture we will be discussing about for random variables. Okay, that how does the Bayes theorem work for the random variables. Okay, so let's hear it. So when we are talking about the Bayes rule for random variables, and also previously while defining the Bayes rule for events, I have told you some terms like prior, likelihood, normalizing constant, those kinds of terms. So we will be focusing more on those terms on the basis of random variable for sure. And also there is one important concept that needs clarification, which is a difference between probability and likelihood. Okay, probability and likelihood. You need to have the clear understanding of these two concepts, because definitely if I'm talking about the difference between them, so they are not same. So yeah, probability, we all know, we all are defining the probability from the very starting, that probability is actually refers to possibility of happening something, possibility of happening something. Okay, my writing is too bad, so just bear with it, I speak also, so yeah. And likelihood, when we are talking about the likelihood, then the likelihood refers to the process of determining the best data distribution given a specific situation in data. Okay, so in simple terms, if I'm defining, then probability is basically you're finding the probability corresponding to some data, given that you know the distribution, and in here what you are doing, you are calculating the likelihood corresponding to some distribution, given that you know the data. Okay, basically you are finding the best data distribution under this given data information. Okay, so yeah, let's see it more clearly. For example, now let's take a very simple example. I have also discussed this example in the very starting, that nothing is easier than the coin example. Coin example always solves our problem. Let's say if you are having a coin, okay, and you are doing 10 flips of those coins. Okay, now if I ask you two questions, the first question is, while you are doing the 10 flips, then what is the probability of it having 10 heads? Okay, that when you are flipping it 10 times, you will be getting 10 heads. What is the probability of it? So these kinds of questions will be answered by the help of probability. Now the second thing, if you are flipping a coin, and then while flipping the coin you are getting 10 heads, then the likelihood actually answers the question like this: what is the likelihood that the coin is fair? Okay, so in the first question we are saying that if we knew, let's say if I'm writing here, if a fair coin is tossed, 10 times, is tossed 10 times, then what is the probability of it gaining 10 heads? That is the question corresponding to probability. And in the second question we are saying there is a coin which has been flipped 10 times and I am getting 10 heads, then what is the likelihood that this coin is fair? Okay, so the question is here is about whether the coin is fair or not, given that I have this data that I have collected. And here we are saying we already know that the coin is fair. I want to know what is the probability of getting this data, right? That's what we mean while saying that it's the probability of data given distribution and the likelihood is distribution given data. Okay, you can also see it in this way that when you are saying that if you're having a random variable x which is following some distribution, let's say normal distribution, with some mean, let's say 32 and standard deviation 2.5. Okay, now when I draw the graph corresponding to it, it will be like this. Okay, and this is the center which is 32. Okay, now we have done questions like this in the statistical inference in large sample theory. Okay, that if we want to find out that what is the probability of x lying between 32 to 34. Okay, we done these questions like this. This actually means tell me the probability of this x lying between 32 to 34, given that I knew that mu is equal to 34 and 32 and sigma is equal to 2.5. Okay, so in the probability we are actually calculating this area, that what is this area. Okay, so you can say that probabilities are the areas under a fixed distribution. Okay, probabilities are areas under a fixed distribution. Now in the similar case, when we are talking about the likelihood, okay, so the likelihood is basically if I have the distribution, I have the observed value, then I'm finding the best fit for that observed value. That the likelihood is likelihood of mu is equal to 32, sigma is equals to 2.5, given that x is equal to, let's say, 34. This is my likelihood, and as you can see, depending on the parameters, my likelihood would also change because I can change the parameters. The given thing is only the observed value. So the likelihood, if you can see here, this is the point 34, it will be just this point. It will not be an area under the curve because it's not probability. It is just the point on this curve, which is, you can see from the y-axis, this is the point we are talking about. Okay, so the likelihood is just the y-axis values for some fixed data points. Okay, and when you are doing the statistical inference, if you have done or any, when you are finding the likelihood, then the likelihood describes this likelihood describes distribution of data as if we knew the parameters. Because there is a relation between the likelihood and the density functions, that you can say L of theta given y, the likelihood of theta given y is equal to f of y given theta. That's why when you are calculating the likelihood, we say that likelihood is pi is equal to 1 to n f of y I given theta for all the observed values. Yi, basically y1, y2 to yn are my observed values. Okay, so taking into consideration all the observed values, when you are calculating it, that is your likelihood. So you are actually calculating this, but there is a relation, so you can convert it to the probability function. Okay, and why the likelihood is a good method, or why we studied it? Because likelihood helps us to compare different parameter values within a model. Let's say if I change these parameter values for this particular observed value, this can be a better way for me. Okay, I will find out the best distribution for that observed parameters. Okay, observed values. So that's what the likelihood does. It compares the parameters values. Okay, I think that will be clear, that you can just remember it like this. Like when you're calculating the probability, probability is the data given that you know the distribution, and likelihood is distribution given that you know the data. Okay. Yes. Now let's come to the part where we are going to define the Bayes theorem for random variables. Bayes for random variables. Okay. When we are defining the Bayes for the random variables, firstly know this thing, that in the Bayesian we quantify uncertainty. Okay, we quantify uncertainty about fixed but unknown parameter. Fixed but unknown parameter. Okay, that we do with the help of probability theory by treating the parameters as a random variable. Okay, by treating them as random variable. Okay, so what is happening, I'm just giving a simple overview here for that whatever the prior information we receive, like in the probability for the events, when we are seeing the Bayes for the events, a probability of A given B is my information, given information, or you can say prior information. So here we are saying we have some information, because in the real life when you are having some information, it can be a variable information also, as it can change over the time. So you can frame a distribution corresponding to that information, and that prior information now can be constructed with the help of prior distribution. So firstly, you will say that you are having some prior information, which is basically your prior distribution, because this information is variable over the time. So that's why you are framing a distribution corresponding to it, and that is denoted with the pi theta. Okay. Now the next thing, that is you are having a likelihood. Likelihood I already explained. Likelihood, which is f of y given theta. Okay. Now based on these two pieces of information that we are having, now if you remember here we also have the same scenarios, probability of A, probability of B given A upon probability of B, right? This is the basic conditional that we are saying. So this is my prior in this case, that is my likelihood. Okay, and this is my marginal. I'm defining it for the two events only. You can, because Bayes theorem is just a generalization of it. So if you want me to generalize, I can just say, okay, like summing over all the numbers. Okay, probability of A, like I am having so many events now. Okay, so yeah, prior, likelihood and marginal. Similarly, we will be here that by using these two pieces of information, we will be having our posterior. Okay, and that posterior would be, let's say, P of theta given y or f of theta given y would be calculated as f of y given theta pi theta upon my. Okay, you can see it is similar to what we have studied for the events, but now the difference is we are not having the events, we are having the random variables. So the prior information is in the random variables, and also the posterior information is a distribution. Okay, Prior is a distribution, posterior is a distribution. Everything we are dealing with that are the distributions now. Okay, so basically we are treating the parameter theta and y, data and the parameter, both as random variables. Then we are framing this Bayes theorem, where this pi theta is basically the prior information similar to this case, and this f of y given theta is my likelihood, and this m of y is, you can say, is the marginal or a normalizing constant. Normalizing constant. Okay, now most of the time this more normalizing constant can be ignored because as you can see, it does not depend on the parameter. So similarly, I can rewrite this Bayes theorem as, okay, rewrite it as f of theta given y proportional to f of y given theta and pi theta. Okay, and the reason behind it, because the normalizing constant or marginal does not depend on the parameter, so we can write it in this format. Okay, now try to understand the each and every term very clearly. You are having this as your prior, this is your prior distribution, which is used to summarize uncertainty before observing the data. So the information we are having before collecting the data and making the distribution from it, that is my prior distribution, observing the data. Okay, this term is your likelihood function, which is actually the distribution of observed data given the model parameters. You can say, okay, model parameters. For not getting confused in the definition, see, if I am going to write this into the likelihood function, we will be writing L of theta given y. But I have already shown you the relation. But when I am writing this into the probability density function, we will be writing as like this. Okay, that is a relation here. Okay, so the distribution of observed data given the model parameters, and this likelihood function is actually a very important link from going prior to posterior, because this is the link which connects the data and the parameters. Okay, then you will be having posterior, which summarizes the uncertainty about parameters given the data and prior. Uncertainty about parameters given the data and prior. Okay, so I think the definition would be clear now. Okay, that is the Bayes theorem that we are going to look. Okay, now let's consider some questions corresponding to it, that how are we going to actually use it while we are doing the questions. So let's see it. Let's take an easy question first. Let's say if you are having, suppose the random variable x takes two values 0 and 1. Okay, having the PMF is f of x given theta is equal to 1 minus theta for x equal to 0, and it is theta for x equal to 1. Okay, and parameter theta is discrete random variable having the PMF having the PMF as g theta, which is equal to 0.25 for theta is equal to 0.4 or 0.6, and it is 0.5 for theta is equal to 0.5. Okay, now the question is, then what will be the posterior for theta given that x is equals to 0? Okay, so you need to calculate the posterior corresponding to the given information that x is equal to 0, which is, you can say, f of theta is equals to theta I. Basically, for different values of theta it is taking. Given that x is equal to 0 is equal to, you can say it is g of theta is equals to theta I, and f of x is equals to 0 given theta is equal to theta I upon the marginal corresponding to it, f of x is equals to 0. Okay, so the first thing that you need to calculate here is the marginal corresponding to x equals to 0. Okay, that you can calculate f of x equal to 0. What will be it? It is just by the additional theorem of probability. It will be, you can say, summation of g theta is equals to theta I, f of x equals to 0 given theta is equals to theta I, for I is equals to 1, 2, 3 because I am having 3 theta values. Okay, now let's look at one by one. What is g of theta is equals to theta 1? Okay, g of theta for theta 1, let's say this is my theta 1.4. Okay, so for this 0.4 I am having g of theta value as 0.25. Okay, so we are going to put 0.25, and f of x equal to 0 given that theta is equals to theta I. Okay, for this f of x equals to 0, f of x given theta, given that theta is equals to theta I. So in the first case we are calculating it for 0.4. So that will be 1 minus 0.4. If you want me to rewrite it, that means g of theta is equals to 0.4. Okay, and f of x equals to 0 given theta is equals to 0.4. Okay, see it here, that's what it is going to happen. Similarly, you can calculate it for the 0.6, and that will be g of theta is equal to 0.6, which is again 0.25, and g of f of x equals to 0 for given that theta is equal to 0.6, that is 1 minus theta, so 1 minus 0.6, plus g of theta is equals to 0.5, which is 0.5, and here again for x equals to 0, 1 minus 0.5, and that will be, let me just simply do some simple mathematics, 0.25, 0.6, 0.4, and this will be 0.25, so plus 1, and that is coming out to be twice of 0.25. Okay, that is my marginal for x equals to 0. Now let's find out this posterior probability for different values of theta. Okay, so we are having 3 values corresponding to theta, like 0.4, 0.5 and 0.6. Let's just calculate them one by one. So for the first portion, f of theta is equals to 0.4 given x equal to 0, and that will be g of theta is equals to 0.4, f of x equals to 0 given theta is equals to 0.4 upon the marginal of x equals to 0, and that is coming out to be this thing we have already seen. G of theta is equals to 0.4 is 0.25. Okay, and for theta is equals to 0.4, f of x equals to 0 is 1 minus theta, so we are going to say 0.25 and 1 minus 0.4, and the Marginal corresponding to x equals to 0 is twice into 0.25. So twice into 0.25. This would cancel out and we will be having 0.6 by 2, which is 0.3. Okay. Now they are asking for this given information x equals to 0. So basically you need to find it out for all the three values corresponding to theta. Like f of theta is equals to 0.5 given x equals to 0. Similarly, you will do it for f of theta is equals to 0.6 given x equals to 0. By using the same procedure that you have done, if I do it directly, then I can see that it is 0.25, 0.25 and 0.5, 0.5 and twice of 0.25. The procedure is definitely same. Okay. 1 minus, okay, sorry, 0.5. This was 0.5. Okay, now this will be 0.25 and they will cancel out, and this is 0.5. And for theta is equals to 0.6, they are having again 0.25, 0.4 upon twice of 0.25, and that is coming out to be 0.2. Now there is one thing I want you to see, that here f of theta given x equals to 0, that is the posterior, which is actually a complete probability density function, because if you can see, the sum of probability here is coming out to be 0 for coming out to be 1 for different values of theta we are using. 0.4, 0.6, 0.6 and theta 0.5. Okay, you can calculate this one by just subtracting, or you can calculate this one by just subtracting the others two, like 0.3 minus 0.5, that will also be 0.2. Okay, that is the same thing. Now if they will ask you for x equals to 1, given that the situation is x equal to 1, you can similarly calculate it. But yeah, here the case is defined for when you are having a discrete prior information. Okay, as you can see here, you are given a discrete random variable while defining. Now when you are calculating the Bayes theorem for random variables, it is not necessary that both random variables are going to be discrete or both going to be continuous. It can happen that one of the random variable is discrete and the other is continuous. Okay, or maybe theta is random discrete and x is continuous, or theta is continuous, x is discrete, or maybe both continuous, both discrete. Okay, either way is possible. So we are going to use the simple probability theory, whatever we have studied, to calculate all the scenarios we will be facing. Okay, so let's just try that. If you are having a continuous random variable for the parameter, so basically if we are having a prior of continuous type for the same problem, okay, for same problem, if prior is of continuous type, okay, let's say you are having a prior as g of theta is equals to 1 for theta lying between 0 to 1, then what will be the posterior? The formula for the posterior basically remains same, that f of theta given x is equal to g theta f of x given theta upon f of x. Okay. Now for calculating this posterior, I need to find out the marginal corresponding to x. I am using the same distribution that has been given here, f of x given theta. Okay, the likelihood is basically same that we are using. Now we have given that f of x given theta is equal to 1 minus theta for theta, for x equals to 0, and this information is theta for x equals to 1. Okay, and we need to find out the marginal corresponding to x, and for finding out the marginal, we firstly need to find out the joint of theta and x, then we can find out the marginal. So for finding out the joint corresponding to them, we have this information that f of x given theta is equal to f of x comma theta upon f of theta. So basically your, sorry, g of theta. So your f of x comma theta can be expressed as g of theta, which is 1, and f of x given theta. So basically the joint is equal to the conditional, because my prior distribution is just the continuous distribution and it is taking the value 1, so they are coming out to be same. So from here we can say that f of x comma theta is equal to 1 minus theta for x equals to 0 and theta for x equal to 1. Now from this we can calculate the marginal corresponding to x. Okay, so marginal corresponding to x is basically 0 to 1, okay, f of x comma theta into d theta. That's how we calculate the marginal. If I want to find out the marginal corresponding to x, I will integrate it corresponding to theta. Okay, so yeah, now there are two values corresponding to theta for x equal to 0 and for x equal to 1. So it is taking two, it is divided into two functions. So we will also divide it into two functions, 0 to 1 for 1 minus theta into d theta and 0 to 1 for theta into d theta, as you can see. Okay, so while integrating this portion, let me just remove this one. So yeah, while integrating this, we will be getting theta minus theta square by 2, 0 to 1, and that is coming out to be 1 by 2. And here we will be having theta square by 2, 0 to 1, that is also coming out to be 1 by 2. And this is for x equals to 0 and this is for x equal to 1. Okay, and that is, you can say, this is the marginal we are getting. So based on this marginal we can find out the posterior. Okay, f of theta given x, let's give it a shot. F of theta given x, okay, that is equal to, now you will also see it in two formats, because you are having for x equals to 0 and for x equals to 1 also. Okay, for x equals to 0 and for x equal to 1. Okay, so my posterior is g theta f of x given theta. Let me just write it here also. We are having it as g theta f of x given theta upon f of x. So we are just trying to put it here that g theta, which is actually 1, f of x given theta for x equals to 0, that is 1 minus theta, and for x equals to 0, f of x is 1 by 2. Okay, so this thing is for x equals to 0 and theta being between 0 to 1. That is coming out to be twice of 1 minus theta. Similarly, g theta, which is 1, f of x given theta for x equal to 1, f of x given theta was theta, I think, yes, theta upon f of x was 1 by 2 for that also, that is 2 theta. Okay, so this is the posterior distribution that you will be getting for this case in the continuous prior. Okay, I think this one is quite good. Okay, now let's try some another problem. Let's say this is a quality inspection problem. Yeah, so let's see it. The question is, a manufacturer claims that the shipment contains only 5% of defective items, but the inspector feels that in fact it is 10%. The defectives are 10%. Now we have to decide whether to accept or reject the shipment based on theta, where theta is the proportion of defective parts before we see real data. So the theta is basically the prior information, prior parameter before we see data, actual data. Okay, so now they are saying let's assign a 50-50 chance to both suggestions. Okay, and what are these two suggestions? We are having two suggestions that the defectives are 5%. So pi for theta is equals to 0.055%, and pi for theta is equals to 0.1 when they are saying the defectives are 10%. We are assigning the equal chances to both of these defectives, that these defectives are equal to occur. So we are saying the probability of occurrence of these proportion of defectives are equal as 0.5. Now a random sample of 20 parts has 3 defectives in it. Okay, now we need to calculate the posterior for theta. Find posterior for theta. Now as you can see, the given information is about the percentage of defective that we are having, that is for when theta is taking the value 5%, which is the proportion of defective which a manufacturer claims, and the inspector claims the defective to be 10%, and we are saying the proportion of the probability of occurrence of these defectives is equal. So this is my prior distribution. Now after this prior distribution that we have assigned before collecting the data, we have this information. We have collected some data of 20 lots, 20 products, and from these 23 products are found to be defective, and we need to calculate the posterior corresponding to this scenario. Okay, so basically given the information about the theta, okay, so firstly we need to find out this thing first, that what will be the distribution of number of defective parts. Okay, now as you can see there are 3 defectives out of 20, so I can just simply say that if x is the distribution, then we can assign it as binomial distribution. Okay, binomial distribution with n, which is 20, and the probability of being defective, that is theta, because it can take any value depending on manufacturing defective proportion and the inspector defective proportion. Okay, so we are going to calculate the posterior when it is find it out that you are having x equal to 3, that is the number of proportion you are having is as x equals to 3, and we are going to find out the posterior corresponding to it. Okay, so before calculating the posterior, okay, let's just find out the likelihood first. Okay, because when you are calculating the posterior, what will you be finding? We will be finding f of theta given x, that is equal to, for x equal to 3 basically, that will be f of x equal to 3 given theta and pi of theta upon f of x equal to 3. Okay, so let's work on this first, that what will be the likelihood function for this scenario. So f of x equal to 3 given when we are taking theta as 0.05, because theta can only take two values, which is 0.05 and 0.1. Okay, so for this scenario we are having a binomial distribution, so that will be 20C3 when theta is 0.05. So in the place of theta here in the place of proportion probability, we are going to use 0.05 raised to the power 3 and 0.95 raised to the power 17. Okay, and similarly for the other value of the theta, which is when theta is taking the value 0.1, you will calculate the likelihood corresponding to it, that is 20C3 0.1 raised to the power 3 and 0.9 raised to the power 17. Okay, when you will be calculating this probability, this is quite a very large number, 0.957 raised to the power 17 and 0.9 raised to the power 17. So for just now you can directly calculate it by the help of calculator, but for the simplicity I'll be using let's say binomial calculator for now. I'm sorry. Okay, so yes, my n is 20. P was 0.05. Okay, 0.05, and for x equal to 3. So firstly you will be having 0.059 0.05958, 0.05958, and for let me just one more time see, 0.1. For 0.1 it will be 0.19012. Okay, you can calculate it directly because you know it's just a simple mathematics, but yeah. Okay, now we are done with the likelihood. Now let's just talk about the marginal. What will be the f of x equal to 3? Okay, now f of x equal to 3, the marginal would be f of x equal to 3 given theta is equals to 0.05 for pi theta is equals to 0.05 plus, that's how we calculate the marginal, for x equals to 3 given theta is equals to 0.1 given pi theta is equals to 0.1. Okay, let's just see, that will be 0.05958 into the distribution pi of theta is equals to 0.05. We are giving this distribution of weightage of 0.5 because we are saying that they are equally likely to occur. So this thing is 0.5, and similarly the pi of theta is equals to 0.5, that is 1, that is also 0.5, and this thing we have already calculated, 0.19012. Okay, and if we simplify this, yes, we will be having 0.12485. Okay, this is my prior. Now for calculating the posterior, we will just apply the formula that we are having, that f of what is it, theta is equals to 0.05 given that x equals to 3. Similarly, f of theta is equals to 0.10 given x equal to 3, and by applying the formula, that is this likelihood, you are, that is f of x equal to 3 given theta is equals to 0.05, which we have already calculated, 0.05958 into f of theta, which was 0.5, upon the marginal, that was 0.212485. Okay, similarly you will calculate this one, that is f of x equal to 3 given theta is equals to 0.1, which is this value, 0.19012, and f of theta, pi of theta is equals to 0.1, that was 0.5 upon the marginal corresponding to it. Okay, while you simplify it, that will be approximately equal to 0.2387, and that will be 0.7613. Okay, now notice one thing. In the previous case, when theta is taking the value when we are defining the prior. Okay, when we are defining the prior, when theta is taking the value 0.05, okay, and 0.10, in that case my prior distribution corresponding to these theta is assigning them the probability as 50-50%. We are saying the probability of occurrence of these 5% and 10% defectives are equally likely, and this was my prior, sorry. Now after considering the data into account, we have updated our probability. Now we are calculating the posterior probability for theta given x equal to 3. This is my posterior. Now for the 5% of defective we are having 0.2387 chance, and for 10% of defective item we are having a posterior probability as 0.7613. So as you can see in the beginning, when we are having a prior information, there is no preference to any of the defectives. We are assigning them as equally likely occurrences for both of these defectives, but after taking into account the data, there is a difference in the preference of the proportion of defectives, as we can observe that we will observe a rather high proportion of defective, uh, like for theta is equals to 0.10, there is a high probability in comparison to the for theta is equals to 0.05. Okay, so the theta is equals to 0.10 is 3 times approximately. I think it's more likely than the other one. So the previous information is they are equal, and now we are having the updated probability that is showing quite the difference between these two probabilities. Okay, so that's what the posterior probability does. Now there is one more important thing here is it's not always very easy to just choose your priors. Okay, like in this case we are having 5% effective, 10% effective, and we are assigning them, we are assuming that they will be having equally likely chances to occur, but it's not always easy to find out the priors corresponding to the given information, and for that we are having different scenarios and different prior methods to calculate that how should we choose our prior information and what will be my prior distribution. Okay, so we will be seeing the next thing as choosing the prior, choosing prior, and what are the types of prior that you will see. Like you will have conjugate priors, informative priors, non-informative priors. Okay, in the conjugacy you will be seeing beta binomial priors and different kinds of priors basically. Okay, so we will be focusing on that part, that when you will be dealing with the real life data, then what priors you should choose, or you can say what types of prior we actually have right now. Okay, yes, so that's all about today's lecture. Let's meet with a refreshing new topic in the next class then. Have a nice day. Bye.